Afternoon to everyone. Today I'm going to present non-halogenated surface active ionic liquids as electrolytes for supercapacitors. And currently I'm working as a guest scientist at Stockholm University. Before starting the presentation, I would like to share that from where I'm at. So I'm working here in Sweden, town Luleå University of Technology, and this is my research group. I'm here in the middle and work with the Professor Oleg. You can see. Can you see the cursor?
Sorry?
Can you see the cursor, or do I need to change it to laser point?
Yeah, we are able to see the cursor. That's all
So
right.
this is Professor Oleg and Jutkin. Now, why we should consider the ionic liquids when there are already a lot of electrolytes available? So the main reason for using ionic liquid is when we talk about something for electrolyte, we need conductivity, a higher conductive material, and ionic liquid contains cations and anions, and asymmetric and large size of ions, which make them low melting point salts, and they have the exceptional physicochemical properties and application in different fields. Like the properties is low volatility and low flammable, less hazardous and less toxic. Mostly they are highly chemical and thermal and electrochemical stable. One of the most important properties, designability. We can design or choose the cation and anion according to our requirements. There are a lot of combinations available, or we can prepare a lot of combinations. They have the high surface activity, high conductivity, and high polarity. And due to these unique properties, ionic liquids have a wide array of the applications like catalysis, synthesis, and medicinal industries, petroleum industries, electrochemistry, and lubrications. On top of that, most of the ionic liquids are green solvent, environmentally friendly, and alternatives to the volatile organic solvents. And some of the ionic liquids are immiscible with the organic solvents and provide a non-aqueous polar alternative to biophysics systems, which is very useful in pharmaceutical and catalysis. Here we'll be talking about the new class of ionic liquid, which is surface active ionic liquids. And why we are interested into this, because of the large electrochemical potential window, around 5 volts. They are very highly thermal stable, up to 600 Kelvin. And the most important thing is they can form the nanostructure on the electrode surface or the hydrophobic electrode surface. And due to this phenomena, they can store more energy at high temperatures as compared.
Je fais la montagne en même temps que je fais ça. Tu vois, la montagne. C'est quoi ça pour qui?
Sorry.
Yeah, sorry. Please continue.
And because of the formation of nanostructure on the electrode surface, these can store more energy, particularly at high temperatures, as compared to the other ionic liquids. And we have considered supercapacitors over lithium-ion batteries due to some limitations of the lithium-ion batteries, mostly the rare metal, large-scale storage purpose, and high cost. Whereas supercapacitors, we can safely operate them over a wide range of temperature, fast charge, discharge, high power density, and environmentally friendliness. The efficiency of supercapacitor mainly determined by two factors: electrode material, the one which we use to prepare or to store the energy, and the second important factor is electrochemical potential window of the electrolyte. So basically, for supercapacitors, or for the success of supercapacitor, we need to identify a good electrode material with perfect electrochemical potential window, or the stability of the electrolyte. So here we will be talking about the electrolyte, of which is surface active ionic liquid. And this work has been published in the ACS Applied Energy Materials last year. Here we will be using mainly tetraoctyl ammonium, 2-ethyl hexyl sulfate, and iron. As you can see why I said like surface active ionic liquids, because of this anion. This anion has a unique property of having both polar and non-polar group in the molecule. So due to this hexyl group, they behave as a non-polar, but the sulfate group is a polar. And this makes them uh, able to form the nanostructure on the electrode surface. So it's not like they have perfect orientation like a lipid bilayer over the electrode surface as compared to the other ionic liquids, or when we talk about the salts in aqueous or organic electrolyte media. Before considering any ionic liquid or any electrolyte, we must know about their some physicochemical properties like their conductivity, their electrochemical potential window, their thermal stability. So in that only we have, as this is the new class of ionic liquid, there not has been much reports available on this. There is one paper in Nature Materials who talked about this recently, but not so many papers are available on specifically on the surface active ionic liquids. And as you can see here, we have first measured the conductivity of the neat N888 EHS of ionic liquid. And you can see we have done for both cooling and heating from very low temperature to up to 100 degrees centigrade, 373 Kelvin, and it increases. And it's highly viscous. So we thought like to make it to reduce the viscosity. So we can add any organic solvent to it, even though that was not the purpose, but just to check how the organic solvent affects their physicochemical properties like conductivity and electrochemical potential window. So we have simultaneously measured the binary mixture of the surface active ionic liquid with the acetonitrile. And as you can see here, there is a huge difference in the conductivity has been observed. This red solid circles are the binary mixture of tetraoctyl ammonium methyl hexyl sulfate, and the black squares for the neat ionic liquid. And we can see there's a huge change or the large increase in the conductivity has been seen. But there is a limitation. We cannot use this binary mixture beyond 300, because then it's started getting reducing the conductivity. There might be two factors. First is acetonitrile is volatile, and another one is maybe there some aggregates are forming, which has not been, we haven't been focused on that because we were not interested in that. Another good thing of this surface active ionic liquid is this ionic liquid is liquid at room temperature. Whereas if we talk about like a smaller alkyl groups containing like tetraethyl, tetrabutyl, tetrahexylammonium, tetrafluoroborate, all these ionic liquids are solids. And we tried with EHS as well. These ionic liquids are solid at room temperature. But interestingly, with this larger alkyl groups, this ionic liquid is liquid at room temperature. And therefore, it is a better choice as an electrolyte for supercapacitor, because compared to the organic and inorganic solvents, because of the large electrochemical window, which I will show here. So we have measured the electrochemical potential window sequentially from for different windows for this neat ionic liquid. And we can go up to from -3 to +3. I haven't shown here -3, but we can go from -3 to +3. And when we use the binary mixture of this solvent, we cannot go beyond -1 to +1. As you can see, if we go beyond -1 or here from +2, there is some peaks are observed, which might be due to the acetonitrile, but we cannot consider as an electrochemical potential window for the supercapacitor device. So for the safer side, to avoid the polarization, we have used a window from -2 to +2 for the all electrochemical studies for this particular ionic. For the supercapacitor measurements, we have used TSC battery cell. We used the Metro Home Autolab potentiostat, and the system look the TSC battery cell looks like this, which have the current collector, which is made up of nickel and copper. And we prepared the pallets of the electrodes, which was multi-volt carbon nanotubes with PVA, polyvinyl alcohol, as a binder, and active carbon to further increase the conductivity of this multi-wall carbon nanotubes, and the separator as a filter paper. And we have calculated the specific capacitance of the palette material, energy density, and power density by using these formula, which has been well reported in the literature and has been used by different research groups. Now, what was the interesting thing which we observed here is like when we obtain the CV curves, we have seen that at lower scan rate, we got the rectangular shape of CVs at room temperature, like 298 Kelvin. But as we increase the scan rate, the CV distorts, like it goes beyond the rectangular shape. And this might be because of the high viscosity of the ionic liquid at low temperature or at room temperature, and the ions are not completely moving towards the electrode surface. So that's the reason might be possible that we are getting at room temperature rectangular shape at lower scan rate, but not at the high scan rate. Then we have to see then we check the CVs at higher scan rates and higher temperatures. So when we increase the temperature, the rectangular shape even remains up to the higher scan rate as well. So that indicates that yes, it was the issue with the mobility of the ions. And if you can see here, it's this D figure is at around 80 degrees centigrade, and this E figure is at 100 degrees centigrade. And you can see that up to 100 millivolt per second, the rectangular shape remains same. And similarly, we have observed in the specific capacitance values at room temperature, the values are very low with increasing the scan rate. But when we increase the temperature, we can reach up to from 100 to somewhere around 170 farad per gram, which is very good and gives it another feature to this ionic liquid, that because most of the ionic liquid or electrolyte cannot be used in a very wide range of the temperature. But this ionic liquid can be used from room temperature up to 100 degrees centigrade, or maybe we can go further beyond, but there was some limitations with the instrument temperature, so we haven't done that. Then we have measured the electrochemical impedance spectroscopy of these ionic liquids in the neat system as electrolyte and binary mixture. And as you can see here that at lower temperature, the resistance, solution resistance, charge transfer resistance are very high for neat solvent. But when we move toward the binary mixture, these values are very low, as we can see in the high frequency region and the semicircles in the inside as well. So here are the values for better understanding. So we have also compared with the 6 molar KOH, which is aqueous solution, the neat ionic liquid, and the binary mixture of ionic liquid with acetonitrile. And what we have observed interestingly is, as I told you that this ionic liquid is highly viscous at room temperature, and the charge transfer and resistance and the solution resistance have the very high values, 1248 and 1603. But when we increase the temperature, the charge transfer resistance even becomes lower than the aqueous electrolyte at room temperature, which is 148 and it is 34. So even it is 56 at 80 degree, 42 at 60 degree. So it's an indication that at high temperature, this electrolyte is even behave better than the aqueous electrolyte at room temperature. And also the binary mixture, if we want to use it like very low temperature, which is minus 20 degree, so we can use the binary mixture of this ionic liquid. So it gives us a very wide range of temperature to use this ionic liquid or electrolyte. Here we can say for the comparison, the specific capacitance for the three studied systems, 6 molar KOH, binary mixture of ionic liquid with acetonitrile, and the neat ionic liquid. And we can see here the specific capacitance values are very high for aqueous electrolytes as compared to the binary mixture of ionic liquid and the neat ionic liquid in the whole range of temperature. This might be because of the in aqueous electrolyte, we have a smaller ions and a high concentration of ionic liquids, whereas for binary mixture of the ionic liquid and neat ionic liquid, the viscosity is very high and also the ion size is very high. So that might be possible that it has been getting difficult for the ions to go inside the pores of the electrode materials. But when we talk about consider the aqueous electrolyte, the electrochemical potential window is very low. It's just 1 volt. And for binary mixture of ionic liquid and acetonitrile, it's 2 volts. But for neat ionic liquid is 4 volt, which makes a lot of difference in the energy density, and which is important parameter for electrolyte to be used in supercapacitor devices. Even though the specific capacitance is low, but these values are at room temperature, so we can use at like high temperature with the high energy density and high power density. And that's the reason that this ionic liquid is getting more and more interest as an electrolyte for the supercapacitor devices. And also we have checked this capacitance retention of CV cycles at different temperatures, 298, 333 and 373 Kelvin, and we can see that the retention is more than 90% at even up, at the very high temperature 373 Kelvin. The Regon plot, which will give us its energy density versus power density plot, and it gives them how this surface active ionic liquid is important and outperform the other two electrolytes as compared to other reported ionic liquids. These black circles and blue black squares and blue circles shows aqueous and organic electrolytes, which are lying somewhere in the low power density and low energy density region. Other ionic liquids have a higher energy density but very low power density. But when we consider the neat surface active ionic liquid with increasing the temperature, so basically we are increasing both energy density and power density. And that's very interesting phenomena. And this might happen because of the orientation of the ionic liquid or surface active ionic liquid on the electrode surface is different as compared to the aqueous or organic electrolytes or other ionic liquids which are not able to form the nanostructure on the electrode surface. We have also carried out this study on the other ionic liquids with the same anion, e.g. EHS minus, C6C1 imidazolium, tetrabutyl phosphonium, and trihexyl tetradodecyl phosphonium. And we have seen that even by changing the cation from tetraoctyl ammonium to C6C1 imidazolium or tetrabutyl phosphonium, we further able to increase the energy density and power density of this surface active ionic liquids at higher temperatures, which indicates that the higher size of the alkyl group chains in the tetraoctyl ammonium was responsible for the low values of energy density and power density, because there we have chosen the multi-walled carbon nanotubes, which might have the small pores as compared to the size of the cation. But when we move towards the smaller cation, we are able to increase the charge density and power density of this material. And out of this, this paper is under revision in the Journal of Ionic Liquids. And out of all these studies, we have come to the conclusion that these surface active ionic liquids are non-halogenated, economical, and environmentally benign electrolyte for high temperature applications. As we have seen that at room temperature, we are getting less specific capacitance, but when we move towards 60, 80, and 100 degrees centigrade, these ionic liquids outperform the other electrolytes. Another important factor is the larger electrochemical window. We can use up to 6 volt, but due to polarization, we have used 4 volts, which is very large as compared to the aqueous and other organic solvent-based electrolytes. As we can see here, the specific capacitance of the supercapacitor is 75 farad per gram at room temperature with energy density of 42. But we have seen the twofold increase in the specific capacitance and the energy density of the same material, which is very good. And it is suitable for high temperature applications such as powering energy devices and gas industries and the military and space limitations. These are the publications. As I already informed that we have published this paper in ACS Applied Energy Materials, and second part is submitted to the Journal of Ionic Liquids. I would like to acknowledge Professor Oleg Anjutkin, who gave me the opportunity to work on this new class of ionic liquid, Chemistry of Interfaces Group, Luleå University of Technology, and for constant support and inspiration. Campe Foundations for fellowship and funding for this work, friends and colleagues, and organizing members of this webinar, International Webinar Chemistry 2020, to give me an opportunity to present this work over here. Thank you. Any questions?